Alright, so now we're in section 3, and we've so far thought about functions of several variables, maybe the temperature in a room. Okay, so at any x, y, and z point in the room you're sitting in, you can measure the temperature, okay, and maybe it's this function f. And this is a scalar function, okay. You just get a number. So for each point in the room, there is a number, which is the temperature. But what if you go outside and you think about the wind? Okay, the wind is swirling all around. Okay, so at each point, the wind has direction, and maybe at different points, the wind speed will be larger or smaller. Okay, so there may be a gust of wind, so across the road, the wind is fast. Okay, if you're sheltering behind a building, maybe there is no wind at all. Okay, so at each point, x, y, and z, okay, if you think about the Earth, at each point on the Earth, think about a weather map. Okay, here's a weather map of the UK, and these arrows indicate the direction of the wind. Okay, so at each point, x, y, and z, you don't just have a number, you have a vector. Okay, so this is a vector. Okay, and it's a vector function. Okay, it depends on the position, x, y, and z, and these vector functions are sometimes called vector fields. Okay. All right, so here's an example, another example. So this image shows the temperature of a house. Okay, so this is the surface of a house, and the colors represent the value of the scalar field, so the temperature at that point on the surface of the house. Okay, and this other image shows a vector field in some three-dimensional space. Okay, at each point in the space, the vectors denote some quantity. Okay, maybe like wind speed, and the vectors have magnitude and direction. Okay, so we're going to look at these vector fields and see how our calculus works on these vector objects, these vector functions. Okay, so one example we can think about is, let's think about a cylinder of water. So here's our cylinder. Okay, so this has got water in it. Okay, so this cylinder is containing water. And what I'm going to do is, well, let me first draw an axis. So let's have an x, a y, and a z axis. Okay, let's rotate the water. Okay, so let's assume this is filled. So this is a cup of water filled to the brim. And we're going to put in something to stir the water. So the water's going to rotate. Okay, and let's assume that the water rotates as a whole. Okay, so when we stir it, the whole body of water rotates. Okay, and what this means is if we look down from the z-axis, our cylinder looks like a circle. Okay, it's a badly drawn circle, but you get the picture. Then this is the xy plane. X, y. Then you can think about individual particles in the water, and you can ask the question, how do they rotate? Okay, how do they move? So think about putting like a plank of wood, okay, that's the radius of the cylinder and the height of the cylinder. Okay, and just rotating this plank of wood around the z-axis. Okay, then the body of water will rotate as a whole. So this plank of wood, you can think of it as the pen, it just rotates around. Okay, so this point and this point move from, say I move from here to here. then this point moves this much, and this point moves this much. Okay, but it does so in the same time. So the actual velocity of this point must be smaller than the velocity at this point. Okay, and it turns out that the velocity of any point is equal to minus b times y bx 0. Okay, where b is a constant that's greater than 0, and it describes the kind of speed of rotation. Okay, it governs the speed of rotation. Okay, so faster rotation corresponds to larger b. Okay, we can see that this velocity depends on the distance from the z-axis along a plane parallel to x and y. Okay, so the velocity at this point, say v1, and the velocity at this point, v2, we have that the magnitude of v2 is greater than the magnitude of v1. Okay, so the speed v2 is greater than the speed v1. So let's see that. Let's think about what the magnitude of this is. So the magnitude of v is equal to the magnitude of this vector. And the magnitude of this vector is b times the square root of x squared plus y squared. Okay, and x squared plus y squared is nothing other, and square root is nothing other than the radial distance of your point from the origin, okay, which is you know, at any z. Okay, so we're thinking about planes parallel to the xy plane. Okay, so this will be b times, let's call it rho. Let's call the radial distance rho. Okay, so the radial distance of any point is rho. Okay, this length. So point xy has length rho. Okay, perpendicular to the z-axis. Okay, so this tells us straight away that larger rho means greater velocity. Okay, and we can actually write this velocity in a different way. We can write it v equals b, where b is now a vector, crossed with rho. Okay, and we can actually even do better still. We can cross it with r, where r is the x, y, z. Okay, so if r is equal to x, y, z, and we have b, the vector, is equal to 0, 0, b. Okay, it's a vector that points in the z direction that has magnitude b. So if you're rotating something around the z-axis, so it's rotating in the xy plane, then you can describe that rotation. Okay, you can describe the speed of the rotation and the direction by a vector that is perpendicular to the axis, perpendicular to the plane of rotation. Okay, so in this case, our b is along z with magnitude b. Okay, so let's just check. So what is b cross r? It is, remember how to do cross products? We have a vector b, so we've got 0, 0, b, and r is x, y, and z. Okay, we take this determinant, okay, and this is the ith component. We cover up I, we do 0 times z minus y times b, so we get minus yb in the x component. For the j component, we cover this up, and we do x times b minus 0 times z, so this is xb, and for the k component, we do 0 times y minus x times 0, which is 0. Okay, and you'll see that this matches this. Okay. All right, so we've seen that the velocity depends on the distance from the z-axis that you are. Okay, perpendicular distance from the z-axis. And we can also see that the velocity v is perpendicular to this vector rho also. So let's say v dotted with the vector rho. Okay, where rho, that's called rho a vector that's x, y, 0. Okay, so it stays in the xy plane, doesn't have any z component. Okay, then this will be v is minus by bx 0 dotted with rho x, y, 0. Okay, which is minus bxy, this times this, plus this times this, plus bxy plus 0. And minus bxy plus bxy equals 0. Okay, so v is perpendicular to rho. Okay, fine, let's look at another example of a vector field. Okay, of something that depends on the x, y, and z coordinates, and at each x, y, and z you get a vector. Okay, so a second example of a vector field could be an electric or magnetic field. Okay, so I mean, electromagnetism is the key to all technology, so your phone and your computers work because of electric and magnetic fields. So let's think about a positive charge. Okay, we've got a single positive charge, and the electric field of this positive charge we call E. It's a vector, and it depends on the position away from the charge. Okay, so we go some coordinate r away from the charge, and at this point there is an electric field. Okay, and it's a vector. Okay, because at this point the electric field has some magnitude and some direction. Okay, and it turns out that the electric field of a point charge is a constant divided by r squared. Okay, so it's inversely proportional to the distance from the charge squared, and it's in the direction of r. Okay, this is a unit vector. Okay, so the field lines are radially outwards from the positive charge. Okay, and at each point the electric field is inversely proportional to r squared. Okay, so our field lines look like this. Okay, so the further we go away from the point, the smaller they get. Okay, it should be symmetric. It's not. Apologies. And so on. Okay, and what this electric field is, it's the force on a unit positive test charge. So it's the force on okay, so you have a charge, maybe you've got a proton, okay, and you ask, what's the force on experienced by another particle at this point r? So if I bring another unit positive particle to this point, then what is the force it will experience because of this test charge at the origin? Okay, and that's all this electric field tells you. Okay, and if we wanted, we could write this electric field as a function of x, y, and z instead of r. Okay, in that case, we've got k divided by r squared. And we know what r squared is in terms of x, y, and z. It's just x squared plus y squared plus z squared. Okay, and this is a unit vector. in the direction of r. Okay, so this is a vector x, y, z. Okay, it goes xi plus yj plus zk. But we need to take the magnitude of this, okay, to make it into a unit vector. And the magnitude is just the square root of x squared plus y squared plus z squared. Okay, so this electric field can be written as k over x squared plus y squared plus z squared to the 3 over 2 with a vector x, y, z. Okay, so at every point r or x, y, and z, then we can determine the electric field. Okay. All right, so that's two examples of vector functions, i.e. things that give you a vector for every point in the space. Okay, we now want to see how the machinery that we've developed from the first sections can be applied to these vector functions. Okay, so I'm going to give some, so we're going to develop a little more apparatus that can be used for the later sections of the course. Okay, so let's go.